We've been working with arrow pushing patterns and generally looking at one, maybe two in a row. But most reactions that we'll see in our class and in second semester organic chemistry involve two or more of these patterns strung together in a sequence that we call a mechanism. And basically the mechanism is an organic chemist's roadmap that helps us get from the reactant to the product. So we're going to have to learn how to A, draw these mechanisms, and B, identify, make sure that we have the proper arrow pushing patterns within these mechanisms. So here, similar to Skill Builder 6.4, we're going to ID a sequence of arrow pushing patterns, and I've left off the arrows on my drawings here. We'll also practice adding arrows as we look for changes between the reactant and the product. So if we look at A here, we notice that we have an alcohol on a ring, and we have this acid here. This is just H2SO4. And then we've gained a hydrogen on the O of the alcohol. So as we've said before, it's a good idea to get in the habit of including the lone pairs in your structure, because oftentimes it's those lone pairs that are doing the reacting. So here we're going to add a second hydrogen to the OH using its lone pair. And of course, this is a proton transfer arrow pushing pattern, and we need two arrows here because the original OH arrow needs to break and go back onto the oxygen. And if we wanted to, we could write OSO3H minus, or SO4H minus, which is the conjugate base of sulfuric acid. So that's a proton transfer step, and now we have this structure here that almost looks like we have water attached to the ring, and indeed that's what we have, because we see in the next step we've lost the water and we've created a cation on the ring. And so the next step involves a single arrow push, and since we're losing something, we're breaking a bond and creating two species. That's loss of leaving group. And so we've created water and we've created this cation. And it's important that you remember that the cation has only 3 bonds to it. So there's a hydrogen right there, and then there are, of course, many more hydrogens along the rest of the ring. The last step here apparently forms this double bond, and we form H3O+, so the conjugate acid of water. So we're going to use water as a base, and we're going to gain a hydrogen from somewhere, and we have to figure out where that comes from. Sometimes it's easier if we draw in some of the hydrogens around the point of interest on the molecule we're working with. So here this alkene we know has a hydrogen on each of the carbons that make up the alkene. And if I think about this hydrogen in particular, he's right here on the starting material, but he has a neighbor as well. So there are 2 hydrogens right here, and now there's only 1. So that's where our hydrogen came from. It doesn't matter which one I take. I'm going to use this top one just because it's more accessible and my arrow will be more clear if I draw that. And then, of course, I can't just make a bond to the hydrogen and leave the CH bond alone. I need to draw another arrow, and that CH bond then will drop down and fill in the cation, leaving behind this alkene. So this is also a proton transfer mechanism, and we see 2 arrows here just like every other proton transfer mechanism. Let's look at letter B now. We have acetone and we have OH minus, and it appears that we're putting a CH2 minus on one end of the acetone. It's important to remember that we already have that CH2 with a hydrogen here, just like we have CH3 over here. And so in order to get a negative charge, we need to remove this hydrogen. We can do that with our OH minus base. And of course, this is a proton transfer, requires 2 arrows. The second arrow is forming this lone pair right here. Okay, so now we're at the second one. We've done a proton transfer to get this anion. We've formed water. Now we're going to react another molecule of acetone with our acetone anion. And it looks a little confusing at first, but if we number the carbons, and I'm going to use a different color here, just arbitrary numbers, I'm going to say show that there are 6 carbons here, and of course if I count like that, I also get 6 carbons. You may have used different numbering schemes, but I knew that carbon 5 is an electrophilic site. And how did I know that? Because I can draw a resonance structure of acetone, which shows me that if I have a negative charge on a molecule, that negative molecule is probably going to react with carbon 5 of the second acetone because it has a partial positive on it. And so I know that this is probably carbon 5, and it's got attacked by the negative on carbon 3. So here is my arrow, and I can use this same arrow here that I used in part of the resonance structure to get to this piece. Alternatively, let's pretend I didn't put that first red arrow in there. Alternatively, I could have just attacked the second resonance structure directly. So you see that my anion can attack this cation without any difficulty, and it would form the same carbon structure here. Okay, so I'm going to switch back to green so that we have a bit more continuity here with my first green arrows. I'm going to keep the red arrows as my resonance structure. Switching back to green, you can see there are two options. And so I'm going to use this first one, which would involve two arrows. Alternatively, I could have continued my arrow over here and attacked the resonance structure. You can use either the resonance structure or the original structure to get to this intermediate here that has the 6 carbons in it. Okay, so now we've formed this bond right here, the bond between 3 and 4. And we know that because I used carbon 3, which was an anion, to attack carbon 5 on the new neutral acetone. And this is called a aldol addition reaction. That's not important until we get to chapter 22. So the last step here, well, actually first we need to label this step. So we're using an anion to attack an electrophile, and so of course that's nucleophilic attack. We are taking a nucleophile right here, and we're taking an electrophile. Either one of these resonance structures could be considered an electrophile, and of course this one really tells us why it is an electrophile. So that's where resonance comes into play. If you get stumped, try to draw a resonance structure. It'll probably help you out. So that's nucleophilic attack. And in the last step, I think you'll agree is rather simple. It's just moving a proton from the water onto the O-. And I didn't draw the bond in here. Let me fix that because we want to make sure we have proper structures here. Sometimes we get lazy and don't draw water in all of its glory, and if we do that, we can't draw this second arrow. So it's better to draw water with all its bonds showing, and then we can get to this product here. All right, on to letter C. The first thing that we observe here is that the bromine has left, and so that's going to be classic loss of leaving group, leaving behind a cation and a bromide. And then the second thing is that we observe that the cation has moved from this secondary to this tertiary carbon. And that should not be surprising because that makes a more stable cation, so that's going to be a very energetically favorable outcome. How do we do that? Well, first we need to remember that there's a fourth bond that typically isn't drawn. That's the hydrogen. And so in order to put an empty p orbital here, we need to have a hydride shift. And so this is going to be a rearrangement. And we're the H-, so it's the H with electrons. That's what's moving here. The H- is grabbing its electrons and moving next door, plugging this empty p orbital, giving us a neutral CH2 right there, and leaving behind this tertiary cation. So that's a rearrangement.